many lectures he delivered on various various international and national conferences. The importance of Mr. Kalamcha sir is, according to the Scopus, his H index is above 14 and I index is above 18. The same is for Google Scholar. Both both indexes are same. Due to the present scenario of fuel, his work is very important, and in this globalization in India, particularly in Marathwada region, such research is going on, particularly on hydrogen storage, which is very useful for not only India, but it is useful for international also. Hence, I invited Dr. Vijayananda Govindrao Kalamche sir to deliver his talk. Now, I warm welcome to Kalamche sir, and I request him to deliver his lecture by hesitating time and other restrictions. Please, Mr. Kalamche sir.
Thank you, sir. Am I audible?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Okay. Please make me a co-host so that I can share my screen. Dr. Sarge.
Okay, sir. Okay, sir.
दाढ़ी दिखा रहा है
Okay, sir.
Let me check. Now, still it is disabled. Sarge sir, I have made 2 logins.
Okay, sir. Sir, are you on PC or tab?
Yes, I am on PC as well as on the top tab.
Oh.
Okay, one sec. I will leave this.
Check call. Please check, sir.
Still disabled. Sir, video and audio is clear?
Okay, sir. Yes, yes.
Okay.
Sir, PC now है ना?
हाँ, PC मी म्हणून असेल, PC.
हाँ. Okay, sir.
हाँ, ठीक है, आले आता.
Oh.
Okay, can you see the screen and the video?
Yes, sir. Yes. Yes.
Okay. First of all, I would like to thank the organizers, principal of the Sri Sundarrao Solanke Mahavidyalaya, Mazalgaon, district Bid, for inviting me to give a talk on hydrogen energy, a future's fuel, for this online webinar. And I have been informed by my colleague, friend Om Prasad Sarge, that the audience, they are from all the parts of the country. Maybe I have been reading the chats that they were asking to have the communication in English. So I think I will go in English only. Is it okay? Because outside participants are also there. I think the participants are from south side and also from the north sides. They are also present or they have joined. So I will go most probably in English. If possible, you can interrupt me or you can ask me anything in between also, right? So shall I start?
Okay, sir. Start, sir.
Okay, so I'll be talking on hydrogen energy, a future fuel. The title itself indicate that we want to make this hydrogen a replacement to the current fossil fuels which we are using. Means, you know, we use petrol, diesel for the mobile applications, right? In our vehicles, in cars, right? We use petrol, diesel, so fossil fuels we are using. So basically we are in the hydrocarbon economy, right? Hydrogen is not a direct energy source, but it is an energy carrier, right? So I am going to discuss the basic three aspects from this in this topic. First one is the hydrocarbon economy. Second one, how hydrogen can be used, or how we can make hydrogen a replacement to the fossil fuels, right? And because we want to make hydrogen a replacement to the fossil fuels, we have to make a parallel economy for the hydrogen. Means we have to deal with the every aspect of the hydrogen, right from its production, storage, delivery, uses, and safety parts. And finally, if time persists, I will talk little bit about the computational methods which we have used, and maybe I'll show some of the results which we have already published in the international journals. So first, what is the hydrocarbon economy, right? The industrial revolution started in 18th century, right? And we know that the transportation network, right? It all depends on the fossil fuels which we use, coal, oil, natural gases, and etc., right? And which actually drives the our society. But as per the study, it is found that the energy demand is going to increase because of the increase in the population as well as the increase in the industrialization. So maybe by 2050, the energy demand might get doubled. So we need to fulfill this energy demand required for the global society, not only confined to a particular country or only developed countries. We need to fulfill this demand for entire global community. So what are the drawbacks related to the hydrocarbons or fossil fuels? We can say they are limited, or their reserves, they are limited, right? We know that we have to import the coal and the some other things, right, from the other countries, right? So, and maybe you might be know that everything, the crude oil we get from the Gulf countries, right? So they are the reserves, they are concentrated in a particular region. So we have everyone is depending on the Gulf countries for the supply of this crude oil and other things. The drawbacks of the fossil fuels, you all know that they emits the greenhouse gases, right, which is hammering or destroying the ozone layer, right, which shields the UV rays or the harmful radiations from the sun, right? So another question is that if the reserves, they are limited itself, then how long we are going to use them? Because the energy demand is not going to stop, right? So it is a continuous demand and required for every energy, whether it is developed country or developing country, right? So this is the time where we have to find the alternative to the fossil fuels, right? Because it's our duty that we should think of the future generations also, because they also have to, or they also need the energy for their generations, right? It is not up to only us, right? So whether we can get this alternative overnight, definitely it's not, right? So we have to make extensive research to find out this alternative, right? Because we have to consider all the aspects, right? We need to provide these energy resources in bulk, right? Furthermore, they have to be cost competitive with the fossil fuels. The whatever alternative we are going to have for the fossil fuel, it should be very cheap, or it should at least be compatible with the rates of the fossil fuels, right? And of course, as we know, if we need to fill the petrol, what we do, we go to the petrol pump stations and we refill, right? Means there is a system for the hydrocarbon economy, right? The same kind of system we have to make for this alternative, and that is what we calling to be a hydrogen economy, right? So what do we mean by the proper economic structure? Sorry, means proper economic structure means what? We need to have its production, we need to have its storage, we need to have its delivery system, right? And of course, the final part is the delivery, right? So basically, the main important part, they are the production of the whatever alternative. And to be very specific, here I am talking about the hydrogen as a replacement. So I'm talking about the hydrogen economy. So I'm talking about the hydrogen production, hydrogen storage, and its delivery. And of course, the final one is the safety measures. They are also important, right? Now, what are the other alternatives we have for the fossil fuels? You might have heard solar cells. They are very much now in the market, right? Batteries are there, but of course there are nuclear energy is also one of the option I have not mentioned over here. But all of these they are having some kind of problem. Solar cell technology cannot be used in the mobile application. Mobile means your vehicular application, right? It is very difficult to set a panel, solar panel, so that we can drive a car, right? Further, the thing is that it works only in sunny days. You might be having a solar panel in your houses, right? Solar water heater, right? So they are fixed to one point and they works in sunny days, right? So in a cloudy days, they are limited uses, right? They are having limited uses in the cloudy or night times, right? The another one is the batteries, right? You might have heard just a few weeks or 1 week back in India, in Kashmir, a reserve of lithium is found, right? So batteries, they are also one of the alternative to the fossil fuels or hydrocarbons. But again, it is having some kind of limitation. You might have been seeing in the market that now they are electric vehicles, they are coming, right? And they run on these batteries, but their problem is that the batteries need to get charged after particular time or particular usage. And of course, their range is limited, right? So these are some of the problems associated with the other alternatives like solar cell and batteries. There is another alternative which I have not mentioned over here, that is the nuclear energy, right? The safety issues are there as far as the nuclear energy is concerned. So I'm not gonna talk about the nuclear energy over here. Okay. So what is the best alternative we can have is the hydrogen as a fuel. So how we can make hydrogen as a fuel? Now, can you see the screen clearly? Can you see the screens clearly?
Yes, sir. Yes, sir. No problem, sir. Yes.
So fuel cell is shown. Chemistry people might know this very well. Now, how this hydrogen is going to work as a fuel, that can be understood from the fuel cell working, right? On the left of the screen, hydrogen is shown, right? And we are actually giving input at the anode in terms of the hydrogen. And one membrane is separated between the anode and the cathode. And of course, one catalyst we also need. Now, how this hydrogen fuel cell work out? At the anode, the catalyst, they actually the electrodes, they are platinum electrode. So at the anode, the hydrogen splits into hydrogen ion, means H plus ion, and of course the electrons. Now the H plus ion, they pass through the membrane, that is PEM, proton exchange membrane. H plus ion means nothing but proton, because hydrogen only consists of one proton and one electron. So when it gets ionized, we get proton and the electron. So the proton passes through the membrane and they get collected at the cathode, but at the same time, electrons being negatively charged, they can't pass through the membrane, so they pass through the outer circuit or outer load, and the flow of electron means nothing but we call it to be a current, right? And a bulb is shown there, which is glowing, right? So this is how the energy is created. And on the cathode, the H plus ion, again, they combine with the oxygen from the air and to form the water. Means what? Ultimately, we are putting hydrogen, right? It is splitting at the anode. It is passing through the membrane, getting collected at the anode. At the same time, electrons, they passes through the external load and we get the electricity. On the cathode, the same H plus ion, they combine with the oxygen to form water. Means ultimately what we are getting after the completion of full reaction, the end product is water. And this is the major difference between the use of the hydrocarbon and the use of, or the burning of the hydrogen, or you can say the using hydrogen in a fuel cell. End product in terms of the use of the hydrocarbon is the greenhouse gases, right, which are destroying the precious ozone layer and creating the pollution. Whereas in the use of this hydrogen as a fuel, we are getting water at the end, and the same water can be again utilized to create or produce the hydrogen, right, by electrolysis. But the electrolysis process itself is energy consuming, right? So basically my talk is about it's not about the working of the fuel cell. I am concerned about the storage of the H2, because there are some properties we need to address about the hydrogen, right? So okay, so fuel cell is basically the electrochemical device which converts chemical energy into electrical energy, right? Of course, advantages I have already mentioned. They produces no polluting emissions, right? Sarge sir, screen sharing disabled झाली.
ओके सर, ओके, एक मिनिट सर. ते काही जण ऍडमिट होत आहेत सर. ते तुमच्याकडेच, तुम्हाला होस्ट केल्यामुळे ते तुम्हालाच करता येईल सर. तुम्ही काय करा सर, हे पण करा तुम्ही प्लीज, ऍडमिट पण करा. मी तुम्हाला हे करतो.
कापायला लागेल समोर.
हा सर,
झालं का?
केलं सर. हो.
हा, ओके. Okay, screen. Can you see the screen?
Yes sir.
Okay. So basically fuel cell converts the chemical energy into the electrical energy. Of course, this I have already mentioned, right? There is no polluting emissions out of the use of this hydrogen as a fuel, right, in the fuel cells. This is a renewable source. This is very important one, right? Or the non-conventional energy source, because the conventional energy sources, they are coal and your gasoline and the natural gases, right? And this source is unlimited in its supply. The hydrogen is unlimited, but this other thing is that it is not present in the diatomic form. That is, you will not find hydrogen in a H2 form in the atmosphere, right? it is in the form of some kind of compound, maybe with the carbons or in the form of hydrocarbons or some hydrides, right? So we have to extract it from such compounds, right? So the limitations they are, I have already mentioned. The very much concern part or the research, I think, as far as my knowledge is concerned, the hydrogen economy problem, maybe last 20 years, this problem has been, the scientists and the peoples, they are studying this problem to sort out its production and its storage problem. The second one is the cost of polymer electrolyte membrane, and the third one is the cost of the catalyst. I'll go back to show this figure. Here catalyst is not mentioned, but the cathode, the anode and the cathode which we use, they are made up of the platinum, and you know how costly platinum is, right? So these are the some of the limitations associated with the, you can say, fuel cell or the using hydrogen as a fuel, right? Okay, the second part is hydrogen as an energy carrier, right? As I have already mentioned, we have seen the working of the fuel cell. We are getting the energy, right? And the byproduct is the water. That is very good as far as the surrounding pollution is concerned, right? We are getting byproduct as only water, right? No harmful emission gases are there, right? I have mentioned hydrogen is abundant and generously distributed through the world without or regardless of any national boundaries, right? Means I have mentioned that you will find the crude oil reserves mostly in the East Asia, east part, that is Gulf countries. You will find Arab and UAE and so many other countries are there, right? But it's not true for the hydrogen. You will find the hydrogen everywhere, right? So it is having no boundaries. So we don't have to actually rely on some particular country for its supply. So of course, we have to build up a technology, and we don't need any kind of political access, right, to make a hydrogen economy a future energy system, right, which is based on the hydrogen. So hydrogen can be an ideal replacement for the fossil fuels, but as I have already mentioned, it does not occur in nature as a fuel H2. So it is in the form of metal hydrides or hydrocarbons and so many in terms of some other compounds, right? So this is what I have mentioned, right? So hydrogen is just like electricity, is a carrier of energy, right? So we have to produce it from some natural resources. So steam reforming is one of the process, right? So as to produce the hydrogen. But still in the steel reforming process, right, the carbon dioxide emission is there, right? And whatever all the stuff which we are doing is to avoid the harmful gas emission after the use of the fossil fuels, right? So we must have to think of the production of the hydrogen from the non-fossil or renewable sources like water, right? So okay, so hydrogen economy, as I have already mentioned, that the network roughly consists of three parts. The production means the production of the hydrogen, right? So we have to go with the production from the water, right? And this is the one research area. Those who have completed MSc and might be having some kind of or undergoing some research, the hydrogen splitting at the semiconductor interfaces is one of the research topic, right? You can find many publications regarding this. The second one is the storage. This is the aspect which I have been studying since 2008, right? But my basically work is the computational one, right? So we don't have any such kind of system presently that competes with the hydrocarbon economy in terms of cost, performance, and reliability. Uh, my speed is okay.
Yes, sir. Yes.
Yes, sir, yes.
Okay. So now let's shift the gear to the hydrogen storage aspect, because hydrogen production is the different part related to the hydrogen economy, and the storage is the different part. So I'll focus on the storage part and the aspect related to the hydrogen storage, right? So what are the storage options for hydrogen? Because in the in previous slide I have shown the working of the fuel cell, where we have shown the H2 input at the anode. So but we need to put this H2, or we need to store this H2 so as to give the input at the anode of the fuel cell, right? So traditionally we have three kind of storage options for hydrogen, right? You might see one figure, right? I have shown a car, right? And 4 bars or cylinders they have shown. The size of the cylinder is relative to the car size. On the extreme right, you will find hydrogen is stored in a pressurized manner, or a pressurized hydrogen cylinder is there. So you can see its size relative to the size of the car, and in such a big cylinder, only 4 kg of hydrogen it is stored. The next one from or the second one from the right, is the storing the hydrogen in the form of liquid. So liquid storage is also called as the cryogenic storage. Means it needs a very low temperature, and it is very difficult to achieve such low temperature. And even if you achieve, it is very difficult to use for the mobile applications, right? And the both pressurized cylinders as well as the cryogenic storage, they they are the energy consuming processes, right? And everything we are doing to create a new and clean type of energy, right? So here I have mentioned that the high pressure cylinders, they consumes the 20% of the total energy content, whereas the cryogenic, means liquid hydrogen at low temperature, it consumes 30% of the total energy content, right? I have already mentioned hydrogen is not present in the atmosphere in the diatomic form, means H2 molecule is not present directly, right? So we find it in terms of the metal hydrides or hydrocarbons, right? In which it is chemically bonded to some other compound. So the 2 cylinders on the left, you can see the size of the cylinder in which the hydrogen is present, but in the form of the metal hydrides. So metal hydride means what? Or the hydrocarbons means what? It is in the form of the solid state. So solid state form of the hydrogen is having relatively a small size compared to the traditional storing option in terms of, or in the form of the pressurized cylinders or the liquid hydrogen, right? So you might have understood that how the size of the hydrogen confined in a cylinder, it varies from the pressure cylinder to a cryogenic storage to a solid state storage, right? So basically we are working on the solid state storage of this hydrogen, so that we can have a reduced size of the cylinder or whatever storage tank we have, and that can be delivered at the point of use, right? Okay, so this is the basic which I need to mention in my talk, that hydrogen storage is the problem, And why it is the problem? Because one thing I think I have not mentioned in the slide, but let me tell you that the volumetric density means if you take a hydrogen, or if you want to confine a hydrogen or store a hydrogen gas at normal room temperature pressure, right, you need almost a 3.5 meter diameter sphere to store only 1 kg of hydrogen. Means its volumetric density is too low, right? But it is a very, its energy density is very high. Means mass to energy ratio is very high, but the volumetric density is too low. So basically we are working on to reduce the hydrogen storage tank, or you can say material, or whatever section where we want to store the hydrogen, right? So here I have mentioned that high capacity, or what are the properties that a good H2 storage material should have, that it should have a very high volumetric as well as gravimetric capacity. Means volumetric means mass to volume, and the gravimetric means mass per kg, right? So there is a target set by the US Department of Energy, right? Whatever hydrogen we are storing on the some other material, we need to disarm this hydrogen, or we need to detach this hydrogen at moderate temperatures so as to use it in the fuel cell or somewhere else, right? So we need to have a fast adsorption and the desorption kinetics. And of course, whatever material we are taking, on which the hydrogen is expected to adsorb, it should have zero degradation with repeated cycling, right? So these are the some of the requirements for a material to store the hydrogen in the form of the solid state at the room temperature. And many papers you will find online where many compounds, they have been proposed, they have been studied theoretically, they have been studied experimentally. Some new compounds have been modeled, they have been tested for all these properties, but till today no such kind of material, or no such kind of ideal material is yet to find, right? So the objective of I'll show one result about the H2 storage, and then maybe I think stop and we can have some interaction. And if time persists, I'll show I'll talk little bit about the computational methods if time persists, right? So whatever work we have done, it's let me tell you, this is a thoroughly a computational one, means modeling and simulations we have used, because the thing is that if you want to make some experimental work related to hydrogen storage, right, it is quite expensive one. So a theoretical model can predict, and it can save much more the trial and errors which may occur in the experimental study, right? So basically we have predicted the hydrogen uptake capacity of the organometallic compounds. Now the first part which we have, or which I have talked till now, is the introductory one, and now whatever I am talking is little bit technical one, and something related to the physical chemistry, right? So the objective of this work is to predict the hydrogen storing capacity of the organometallic compounds, right? Chemistry people may know this organometallic compounds, right? To predict the H2 adsorption energies using different quantum chemical methods, right? We have to predict the various temperature range over which this adsorption and desorption is thermodynamically feasible, right? We studied the interaction between the host material and the hydrogen molecule. See, I am specifically, you might have seen in my slide, I have never mentioned H. I am always mentioning H2 because in the fuel cell, we need H2 in a molecular form, right? We don't want it to be an atomic form. We want the H2 in the molecular form, and which is not available in it is not available in that form in abundant manner, right? So we are basically confirming the hydrogen uptake capacity by using different quantum chemical methods with molecular dynamic simulations. For the maybe some PG student might be attending this webinar. So just give me, I'll talk a little bit about these quantum chemical methods. Quantum chemical methods, they are completely based on the Schrodinger equations. Means to solve the Schrodinger equations, there are, I am just talking this in a very introductory manner because I don't want to go into details of this technical part of the quantum chemical methods because it is altogether a different subject. So quantum chemical methods, basically they are the different methods developed by the people to solve the Schrodinger equation, because we might have studied in the chemistry or the physics classes in UG and PG that we can solve the hydrogen equation or the hydrogen, yes, hydrogen Schrodinger hydrogen equation only for hydrogen atom exactly. Schrodinger equation can be solved for the hydrogen atom exactly, right? But for the other higher complex cases, it is not possible to solve exactly. So basically the quantum chemical methods, they are the various methods to solve the Schrodinger equation for a given type of system, right? So this is the paper which we have published in Journal of Physical Chemistry C back in 2010, right? I'll just briefly discuss some of the result about this, and I think I'll stop after that. So basically what we have done here, you might you can see this is the C2H4, and we have capped a vanadium. Means what? The C2H4, right? And we are capping a vanadium, means a transition metal. So we are basically modeling an organometallic compound, and now we want to know how the hydrogen can be, or how the hydrogen molecules interact with this organometallic compound, that is C2H4b, right? These molecular orbitals, they are shown. Okay, so these are the technical details about the study which we have made using different methods. So I don't want to go into the details. I'll just show how. Okay, so now you can see on the screen the organometallic compound is shown, and you can see the hydrogens, they are adsorbed on this organometallic compound. So basically you can see there are four types of, or four figures you'll find. We have studied two organometallic compounds, the C2H4V, and we have made its ionization, and after ionization how it interacts with the H2 molecule that we have seen. So we can see it can interact with 5 hydrogen molecules, right, and which leads to the uptake capacity of 11.32 weight%. Of course, this is gravimetric uptake capacity, and after ionization it interacted with one more hydrogen molecules, that is 6 hydrogen molecules, and increasing the uptake capacity from 11.32 to 13.28, right? So basically this is a very confined results which I am showing, but I just wanted to show that we want to store a hydrogen on such kind of a system so that we can use this hydrogen for the fuel cell applications. And this is the solid state storage of the hydrogen, where the size is getting reduced, because I have already mentioned, or I have shown in the picture, that in the form of solid state, the hydrogen storage, the tank size getting reduced compared to that of the cryogenic or the pressurized cylinders, right? Okay, so some of the calculations are there. I'm not gonna talk about these calculations. We have calculated the absorption energy. I just want to mention one thing is that whatever hydrogen we are going to store on any kind of compound, not specifically the organometallic compound, but organometallic compound have been extensively studied because the interaction of the hydrogen molecule with the transition metal is quite good as far as the other alkali or alkaline metals they are concerned, right? So the interaction of the H2 with the transition metal is good enough so as to get the energies in between the range of the physisorption and the chemisorption. Now, this is very important aspect related to the hydrogen storage on any kind of material. We need to have the energies in between physisorption and the chemisorption. Means we don't want higher energies and we don't even want a very low energy. So we want actually the range of 0.2 to 0.6 electron volt. This is the range of in between the physisorption and the chemisorption, where we can actually desorb the hydrogen at the point of use by just varying a little a temperature, right? So here we have the calculated the absorption energy. This is quite a technical part, so I'm not gonna discuss about this. This is something which we have means we have studied the temperature dependence of these compounds after storing the hydrogen. So these are some of the results. I'm not going into the details because they are very technical one, right? We have studied their kinetic stability and so many other factors. So various parameters they have been studied for this newly modeled organometallic compounds. Here we have capped vanadium on C2H4. Similarly, we have capped titanium, scandium, we have ionized them and we have studied their uptake capacities. Many people have studied carbon nanotubes, functionalized carbon nanotubes, fullerenes, C60, right? And they have been functionalized and they have been studied for their hydrogen storage capabilities, right? So there are yes, this is in this paper we have actually capped titanium and lithium separately on C2H2, right? And we have studied their uptake capacities. I have already mentioned, yes, these are the optimized geometries, Ti acetylene complex and lithium acetylene complex. We have studied their interaction. I have already mentioned the transition metals, they interact, or the compound with transition metal, they interact quite good in a very good manner as compared to alkaline or alkali earth metal, right? Okay, so I think from my side, I'll stop at this point because the further part is very much technical one, so I'm not gonna talk about that. Is it okay?
Okay, sir. Okay. Now the session is open for interaction. Participant can ask question to today's resource person, Dr. V.G. Kalamse, sir.
See, I have taken very primary part. Basically, my aim was to introduce with the problem, current problem or the current scenario associated with the energy. So I have mentioned here two parts. One is the production and other one is the storage related to the hydrogen, because other details I can show you, but they are very technical one and the you might not understand that. So it is better to stop at this point or to stop the discussion at this point. My aim was to introduce with the problem that there is a problem with the hydrogen production and there is a problem with the hydrogen storage, so that now this is the area where you can work out to solve the problem of the storage and solve the problem of the production. This was the basic aim. My aim was to about this talk. Yes, if there are any questions, please.
The session is open for
Uh,
interaction.
Someone is raising hand. Yes, sir, please
Hello,
go
sir.
ahead.
I'm Ketan Gaikwad from
Yes.
KG Somaya College of Science and Commerce, Bombay.
Which
I would
college?
like to ask one question. From KG College of Science and Commerce.
Sorry, your voice is not clear.
Hello, am I audible? Am I audible now? Hello,
One second.
hello. Hello, am I audible?
Yes, sir.
Yes, sir,
Go
yes.
ahead, go ahead.
Okay. So I'm Ketan Kumar Gaikwad from KG Somaya College of Science and Commerce, Mumbai.
Okay, sir.
I would like to ask a question related with this hydrogen production. So what is the maximum efficiency that we can generate hydrogen from the fuel? And is it technically possible to utilize completely all these molecules or hydrogen for our energy sources? And in India, is it possible to practically apply this concept?
See, if you go to the foreign countries, already there are vehicles, but the heavy vehicles, they are running on the hydrogen. But as I have mentioned, there is a problem related to the size, right? For mobile application, just give me a small example. We go to the refueling station and we have a tank, right? And we can easily fill up our tank with the petrol or diesel, whatever we have. But if you go with the hydrogen, the volumetric density is too low. So the size of the cylinder, it ultimately increases. And that's what I have mentioned. The basic research is now going to search a material which can actually store the hydrogen and reduce its size. The first question you have mentioned regarding the production, let me make a clear point. In the very early slide, I have mentioned that there are 2 to 3 ways we can have or we can produce the hydrogen. One is the electrolysis, but the electrolysis process is itself is energy consuming process. So we are keeping it aside. Second one, I think the extraction of the hydrogen from the hydrocarbons. That is again energy consuming, and we are creating a greenhouse gases out of that. So basically, I have mentioned we need to find some sources just like water, and from water you can produce the hydrogen. But from water you cannot go with the electrolysis, because I have already mentioned electrolysis is electric energy consuming process. So there is another area of research that people are trying to split the water at the semiconductor interfaces. Hope I am clear.
Okay, yes, sir. Yes. Okay.
Yes, any other question, please?
The session is open for interaction. Participant can ask question.
There might be some PG students, they can ask the basic questions, no problem.
The participant can ask any question about hydrogen energy, though it is basic in nature. No problem.
You can ask any naive question, right? No problem.
I think there will be no questions, sir.
Sarge sir,
Okay.
please ask one more time.
Okay. We will wait for 2 to 3 minutes, sir.
Okay. Or if some of you may want some part of the slide, I want to repeat. So I can repeat it in 5 to 10 minutes if you want, or if you have any queries in the presentation.
Excuse me.
Yes, go ahead, sir.
So this is Vijay from SRM actually.
Yes, sir.
So what is the software you used for this VASP or any other software for this calculation hydrogen storage?
Yeah.
sir?
We have used Gaussian.
Okay. Would you suggest Gaussian or Any
Sorry?
other it is, which is the best, sir, actually, for doing such
See,
calculations? Which is the best software, sir, for doing the such calculation?
yes, let me give
Sir,
time.
uh,
I'll explain.
mm,
See, there are many softwares. Presently, there are many free softwares available in the market, right? But the globally, the chemistry people or those people who are working in the computational and physical chemistry area, they mostly rely on the Gaussian, right, for the gaseous state calculations. If you want to go to the solid state calculations, there are two options. One is the WASP, Vienna ab initio package, right? And another one is the
yeah.
CASTEP, right? So these are two suggested for the actually WASP is very good for the solid state calculations. Means if you want to create a unit cell or primitive cell and then you want to study there are some characteristics, so you can go with the WASP. WASP is the best one for the solid state calculations. And after that, this CASTEP is there, CASTEP. And for gaseous state calculation, the Gaussian is absolute fine. But there are many other, I think one free software is there that is called CRISDANE. CRISDANE is the one free software which is available for this computational work.
Okay. Actually, if you are doing some photo initiated process, can we incorporate the photo light being followed on the material like that? Can we do in computational also?
See, we can get UV, IR spectra out of these computational calculations.
Yeah, that I got. But what I'm asking is, can we incorporate the light into this reaction chamber?
No, sir.
Properties of light.
No.
Oh.
Computationally, it is not possible because
Okay. So we can
whatever.
do the absorption studies. That's all.
Yes. That we can do. If possible, I can show you one slide where I have shown the vibrational frequencies of these studied compounds. So that we have extracted from the output file of this computational work.
It's fine, sir. I got that point, but so we can't incorporate that photo or some other disturbances into this reaction chamber, right?
See, to be very honest, a single user don't know everything about one software. There are huge number of applications. There are large number of tools. There are large number of codes. There are large number of inputs. They are available. So we have to go through the manual and actually what we wanted to do or what we want to do. Is it there? Is it possible or not? That we can actually understand by going through the manual itself, because there are many tools available in a single software. So one single person, I don't think so that any single person can know everything about one single software.
Okay, sir. Oh, thanks very much.
Yes, any other, please? If you wish, I can show you. Let me.
Sir, can I make you host?
Screen share थांबली का?
Okay, करतो सर 1 minute.
Just 2 minutes.
हाँ सर. So you can share.
Yes. So yes, this is you can see this table 4. We have shown some vibrational modes, that is symmetric stretching, anti-symmetric stretching. There are different kinds of stretch between different CVC stretching, symmetric, asymmetric, stretching between H2 and the transition metal, carbon-carbon stretching, and their vibrational modes I have mentioned, or this is what we have got out of the output file of the this computational work. Okay, yes, any other, please? please feel free to ask the questions. I'll try my level best to give the reply. See, deliberately I have stopped at this point because the further part is quite technical one, and those only belongs to this field, they can understand or they can get a little bit out of it. So that's why I have restricted myself to the introductory part and what is the problem, and that's where I have only mentioned in the presentation.
Participant can ask question. Okay, there will be no questions, I think.
Okay, thank you.
On behalf of Physics Department, Sundarrao Solanki Mahavidyalaya, I thank you, today's resource person, Dr. Vijay Kalamse sir. You gave a very nice session of this today's recent topic, that is hydrogen energy. In recent world, this topic have emerging trend. So on behalf of Physics Department, once again, I thank you. Now I request Mr. KJ Langde sir to give a vote of thanks.
Good afternoon to all. On behalf of all students and staff, I am glad to stand here to express my vote of thanks. I would like to thank our chief guest, Dr. Kalamse sir, this program with his inspirational thoughts. I would like to thank our beloved principals, staff members, students, participants, and last but not the least, our beloved audience for making this function as a grand success. Once again, I thanks and all present here. Thank you.
One suggestion is there. The feedback link provided at 4 p.m. It is mandatory to fill it to get the certificate. Feedback link will be provided at 4 p.m. Thank you. You can quit. Okay. Thank you, sir. Thank you once again. Thanks to all of you.
Sarge, leave karu?
Yes, sir. Yes, yes.
Okay, right.